if you're using any discretization method, you know that more n you have, the more accurate the solution is. But this tells you the bigger the n is, the slower, if you have to use iterative method, the slower the solution is going to converge. So there is a trade-off that, okay, if you have finite amount of computation time, you may you have to balance. If you increase n, you should not only expect your solution, your calculations to be more for each iteration, you would also expect the number of iterations to go up. Or you have to trade off between your discretization error and the error in the solution of the linear equation. So is it possible to have the best in both worlds? Is it possible to both have the fast convergence in the linear solver, in the iterative solver you would get for small n, and also the accuracy you would get for a bigger n? It turns out it's quite possible. The idea is the following. What if you can have a method that uses multiple n's? So one is a finer grid with a bigger n discretizing a PD that is more accurate, and also a small n. You know the solution in your iterative method would converge faster. Okay? And the smaller n would only be able to deal with the solution that can be represented on the coarser grid. But that helps a lot, because if you think of, so let me take an example of a Poisson's equation again. So for Poisson's equation, in 1D, we know that this mode converges the slowest. The rate of convergence of this mode is proportional to n squared, right? So the iterations you need. But this mode is actually the easiest mode to represent on a very, very coarse grid. This mode, you can potentially only use 3 grid points to represent this mode. With 3 points, 1, 2 intervals, the number of intervals equal to 2. And with n equal to 2, cosine of pi over n is something what? Is cosine of pi over 2 is what? 0, right? So for eigenvalue equal to 0, what does it mean? We converge in one iteration, exactly. So the mode that is most difficult to deal with in a very fine grid is something actually that is easiest to tackle in a coarse grid, right? Because the mode is very smooth and can be potentially represented on a very coarse grid and converges in one iteration. And of course, we also have modes that are cosine 2 pi over n, 3 pi over n, etc. These won't be able to be represented on an n equal to 2 grid. But if you can design a series of grids, n equal to 2, n equal to 4, n equal to 8, etc., all the way to our case where n equal to 1024, then for every single mode, there should be one of these grids that you can represent that mode with sufficient accuracy, and that mode would decrease pretty fast, okay, over that grid. So that's the idea of multigrid. And so how do we implement multigrid? So the multigrid is you can represent the procedure as the following. So the x-axis is the algorithm, which means as the computer performs subsequent operations, we are moving along the x-axis. The y-axis is grid. Okay, and if you go up, it's a finer grid, and going down is a coarser grid. So multigrid would always start with the finest grid. So the finest grid is where we discretize the equation, because on that grid we can compute what the right hand side is. Right? On that grid we have the matrix, we have the right hand side. So on that grid we compute the b minus ax that we call the residual. And we can think of all what we are doing in iterative method is to compute is going to have a successively better approximation to x in order to drive the residual r to 0. So this is our first approximation. And then what we are doing in the coarser grids is to solve for the correction. So what is the correction? Solve for delta x such that a times delta x would be equal to this r. Let me see if that's the case. Yes, would be equal to r. So if we can solve a times delta x equal to r, then my x0, because I know that my a times x0 would equal to b minus r, right? So this is a rearrangement of the definition of r. So let's see. Then a times x0 plus delta x0, the correction would be equal to b. Does that make sense? So instead of solving directly for x, we can solve this correction equation a times delta x equal to r, where r is the residual of my best guess yet. And if we can exactly solve the correction equation, we get the exact solution. But even if we can approximately solve this correction equation, we get a better approximation to the solution by adding the original solution with my delta x. And why are we doing this in multigrid? We are doing this in multigrid because as we go to coarser grids, we no longer have an as good approximation to the differential equation as in the final grid. And what we want is that if on the final grid we already have a very good solution, which we hope is true as we move towards the right hand side of the algorithm. If we already have a good solution, we don't want to spoil it in the coarse grid, right? Therefore, we want to solve this correction equation because if we already have a very good solution, the r should be very small. And the resulting delta x would always hopefully give an improvement to the solution instead of the other way. If we keep solving the original equation on the coarse grid, then the coarse grid would always have a mismatch with the final grid, and that's something we don't want. We always want the coarser grids to improve upon the best solution we have on the final grid. We want the whole solution to converge to the solution of the final grid. So when we go to the coarse grid, we want to interpolate. We first want to interpolate the residual R0 to coarse grid. Once we interpolated R0, now my R0 is on the coarse grid. Then I solve my delta x 0 is approximately equal to A inverse times R0. And how do we do this approximation? We can perform a few Jacobi iterations or a few Gauss-Seidel iterations. Remember, on the coarser grids, the modes that we can represent on the coarser grid would always converge faster than how they would converge in the fine grid. Okay, so once we solved this, we can go back and interpolate the delta x0 to fine grid. So this is a two-grid algorithm. We have one fine grid, one coarse grid. We are going to generalize to a multi-grid pretty soon. And then we perform x1 would be equal to x0 plus that delta x of 0 coming from the coarse grid. Okay, and now we are going to do this again, but before we do this again, we want to perform a few other iterations on the fine grid. And what is the purpose of performing a few Jacobi or Gauss-Seidel iterations on the fine grid? The purpose is to get the residual to be at a good enough state, to be smooth enough so that the residual can be interpolated to the coarse grid. All right. Okay. So here we move towards iterations on fine grid, and then go back again. So we go back and compute the residual and interpolate the residual to the coarse grid, and perform iterations on the coarse grid and interpolate the correction back to the fine grid. Okay, so the ingredients that are important is one, computing residual. So that's over here, and the interpolating residual to coarser grids. And the 3 is iterative solver on both coarse and fine grid. And 4 is interpolating not the residual but the solution to finer grid. So once we have all these 4 components, we can put together a multi-grid solver. All right. Any questions so far on this overall idea? Yes?
Why do we need to interpolate from the fine grid to the coarse grid? Is it the coarse grid that is a substructure of the fine grid, and then we can only pick up the values on the coarse grid without interpolating? Or?
Oh yes, actually, if you can design the grid so that you don't need the interpolation, that'll be great. So then the interpolation is a trivial interpolation. That's right.
So just picking the values.
Just picking the values, right.